It's Professor Robert Needing. Welcome to Math 168, and this is my exam number 2 review. So if you have your exam review that's posted in class, you want to grab onto that, and we'll go through and see how many things we can get identified from here. This may go just a little quickly. However, though, at the same time, remember, you can always pause it, clear it, and go back to it and rewatch it a couple of times. So get yourself some popcorn, get yourself something to drink, and hang on for the ride. First question says, identify each of the following as a parameter or a statistic and give the correct notation. We're talking about a correlation between height and arm span, and it doesn't matter really what it is, for all players. So the identifiable piece here is all players. And since we're dealing with all players, we're dealing with a correlation value, and a correlation value is a row value. Kind of hard to make the row value, but there it is right there. Number B, proportion. So now we have a proportion value, and that proportion value is of all students, of students who smoke in LCC based on the data from my class. My class is not all of LCC, so therefore now we're talking about a p-hat situation. Look at the correlation between, so we're back to correlation again, between the prices of textbooks and the number of pages based on just simply 25. This is a statistic, and since this is a statistic, this is going to be an R value. It goes along with the row value, but it's for a statistical average. The average commute time, so we're talking about average, so it's either mu or X bar. For employees at a small company based on an interview with all, keyword here is all. This is a mu calculation. We have the average gas price in Minnesota based on prices from randomly selected people. Again, this is an average, but it's an average of a statistic, not of an entire group. Last one we have on here is letter F, the proportion of students who enrolled in all community colleges in Ohio in the fall of 2018 semester based on data on all student enrollments. All students, got a little tricky here, all students, keep reading, enrolled at LCC. But we're talking about everybody in Ohio, so we are still a sample, we are still a p-hat. Almost got us on that one, didn't they? On section 2, we're on to identifying whether each of the following samples is a possible Bootstrap sample from the original sample. And the original sample is given at the value of 20, 24, and 19, 23, 18. I'm going to undo that because I really don't like what I just did right there. And I'm going to grab a new color. So give me another color here. That's a little bit better. Not awesome, no. All right, so first things first, let's see what we see. First of all, I see that there is a 22 in the set given. 22 is not in the original, so therefore 22 is not possible. In the next one, I see all of the same data sets. It's the same size. Therefore, it's possible. Remember, it has to be of equal size n, and it has to come from the same values that I start with. In the next one, there's a 21, which was not in the original, therefore not possible. In the next one, they can be all 20, because 20 is in the original set. It's right here, so therefore all 20s is possible. In the next one, all numbers are occurred. It still has a set of 5, and it's possible. The next one is clearly not possible, and the reason being is because it's missing that last term right there. It's only got 4 n values, and n value of 4 does not equal n value of 5. Question number 3, fill in the blank. In October of 2012, survey of 7,786 randomly selected adults living in Germany, 5,840 said that they exercise for at least 30 minutes, 3 or more times per week. The sample is... Well, the sample taken is from the value. So when we are sampling from here, we are sampling 7,786 Germans. And it's important that we identify who we are sampling. We are measuring a proportion because it says, and I'll find that value so I'm not writing there. It says they exercise for at least 30 minutes time per week. The proper notation is p-hat, because remember what we're doing is we're taking 5,840 of them and dividing them by 7,786. The proper notation here is p-hat, and the best estimate for this particular population is 0.75. Again, how do I get that? I take the 5,840 and I divide them by the 7,786, and that leads me to the proportion of 0.75. Number 4, according to the U.S. Census, 71.6% of Americans are age 21 and over. The provided figure shows the possible sampling distribution for proportion distributions of age 21 and over for sample sizes of 50, 125, and 250. What they want us to do is line up which picture goes with which sample size. Remember, the larger the sample size, the tighter the distribution. So if I look at the distribution of these values, letter B is the furthest spread out. It has the largest standard deviation. It's going to come from the smallest sample size. So B is going to come from the 50. If I go to the one which is the tightest, meaning the least amount of standard deviation, that's letter A, and letter A is going to have the greatest number of n values because it'll have the best distribution. And the only one left remaining here is C at the 125. Moving on to question number 5. The sampling distribution shows sample proportions from sample sizes of n equal 3,5 with 1,000 bootstrap distributions. Make sure this is not in our way, and we should be okay here. You can read it. And the question is, what does one dot on the sampling distribution represent? Well, any one dot on the sampling distribution is n equal 35. There are 35 different n values in any one of those dots sitting in there. Estimate the population proportion from the dot plot. Okay, well, if I find the center approximately, the center is approximately 0.63. Estimate the standard error of the sample proportion. People have a hard time with the standard error, but if I look at this particular one, it looks like that I'm breaking it up into approximately plus 0.7 plus another 0.7, minus 0.7, minus 2 0.7s. So my approximation of my standard error, excuse me, couldn't get that out of my mouth, standard error is 0.07. Using a sampling distribution, how likely is p-value of 0.65? Well, I'm going to go find 0.65 and I'm going to put it on the chart. It would be about here. This would be about p hat 0.65. It's clearly under the curve. It's within one standard deviation, and it is definitely reasonably likely that it will take place. It's in the 95% problem within inside of there. Problem E, using the sampling distribution, how likely is P 0.45? When we're looking at 0.45, we have to do exactly the same thing. We have to go to 0.45. We have to find it. It is clearly down under in the area. So 0.45 is down on the outside tail. P hat 0.45. So now when I'm looking at 0.45, it is unusual, but it definitely could happen occasionally because I see dots out there. How likely is p hat 0.98? Get myself a new color here. 0.98 is off the chart over here somewhere like this. P hat 0.98. So if I have a 0.98, this is going to be a sample statistic that would not happen very often. It would be extremely unlikely, but we would never say that it does not take place. If the sample size N65 had been used instead of 35, which of the following would be true? Well, remember that if we use a larger sample size, the curve will come in. Since the curve will come in, the sample statistic would be a better estimate of the population parameter, letter B. We get better data if we run larger sample sizes. N increases, better data. If sample size of n equals 65 had been used in 35, what else would be true? It would also say that the sample statistic would have less variability. Remember, the curve would come inward towards the center, which is the true population parameter. Question number 6. In 2010, the Center for Disease Control and Prevention estimated 9.4% of children under the age of 18 had asthma. They reported a standard error of 0.35, assuming that the sampling distribution is symmetrical, find the 95% CI. Well, that means that we take the given distribution of 9.4, we're dealing in percents right now, and from there we're looking to distribute on a level of 0.35%. That means we're going to add and we're going to subtract two 0.35s, because it's two standard errors added and subtracted from the center of the curve. Therefore, we would wind up with a CI which floated somewhere between 8.7 and 10.1. Again, center, 9.4, plus and minus two standard errors, which would be the same as plus or minus one measurement of error. A sample of 148 college students reports sleeping an average of 6.85 hours on a weeknight, with a margin of error, so there's an ME of 0.35. Based on the information, identify each of the following as plausible or not for the average amounts of sleep. Well, first thing I have to do is I have to look at the question. I just have to say, okay, fine. They reported 6.85. 6.85. 6.85 is going to be plus or minus one margin of error. The margin of error is 0.35. We do not double the margin of error. We only double the standard error, which means I would be somewhere between 6.5 and 7.2. This is critical in order to get this data. So my first one, 6.6, is inside of that data, plausible. 7.5 is outside of that data, not plausible. 8 hours is outside of that data, not plausible. We find the CI, and if it doesn't fit within inside of the CI, then the plausibility is no. Percentiles of Bootstrap distribution are provided. So we see some values that are provided in here. Use the percentiles to report the 95% CI. Well, remember that a 95% CI, is subtracted from 100%, leaving 5%. But remember, 5% has to be divided by 2 because of each tail, leaving 2.5% on each corner or on each tail. So we come in from the ends 2.5%. 2.5% puts me at 97.5 and 2.5. So for my first solution, 6.322 to 8.082. For my next one, I'm going to do a 90%. Well, I'm going to do everything the same, but now I know there's 10% left over. And 10% divided by 2 is going to be 5% on each side. So now I'm going to find 5% on each side, which is going to put me at 7.947 and 6.438. So 6.438 up to 7.947. And for my last one, I have an 80%. Well, 80% from 100 is 20%. 20% divided by 2 is 10%. Now I come in 10% on each end, and when I come in 10%, and I go up 10%, I'm at 6.593 to 7.780. Moving on to the next question. I'm only on question 9, and I already feel like I need a snack. Percentiles of Bootstrap distribution based on 5,000 samples are provided. Use the percentiles to provide a 92% confidence interval level for here. Remember that if we're providing a 92, that means there was 8% left over from 100. Divided by 2, really bad division sign there. Divided by 2 means 4 percentile at each end. 4 percentile puts me at these two statistics. Interpret the 92% confidence interval in the context of the situation. So now in the context of the situation, that means we actually have to use some words associated with it. And I'm not going to type these. I'm going to read these. We are 92% confident that the true mean amount of time for all U.S. adults spent watching the presidential election on election night is between 65.160 to 95.780 minutes. Remember, the context of the situation is in the context of the problem, using the parameters that were given. Question 10. In a poll conducted before a Republican presidential primary in Michigan, 134 of 420 random voters indicated they planned to vote for Mitt Romney. Well, right away, that means I have a p-hat value, because it's a proportion value, of 134 people who are going to vote out of 420. When I do the calculation on that, that's 0.319. That's my point statistic for this question. Use appropriate notation and compute the best point estimate. That's the one I just did. So p-hat equals 0.319. Suppose the article describes a poll, says that the margin of error of the statistic is 0.045. So what we'll do is we'll take the 0.045. It's a margin of error. So we'll take 0.319, and we will add and we will subtract a single value of 0.45 in order to calculate our interval estimate. Our interval estimate would be 0.274 through 0.364. Interpret this, again, in context. If you look at number 10, the interpretation is we are 95% confident that the true proportion of all, that's important to all, Michigan voters to plan to vote for Mitt Romney is between 27.4, so notice turn the decimal into a percent because we're writing about it, to 36.4, again, a percentage because we're writing about it. Number 11. If the proportion of smokers between male, should say male, not make, male and female students, P of M minus P of F is 0.05, and the standard error is estimated to be 0.056, find and interpret the context of the data situation for a 95% confidence interval level. Okay, so that means that I'm going to take 0.05. I'm going to add and subtract. It's a standard error, so I need two standard errors, and it's 0.056. When you make the calculation for that value, you're going to get, what are you going to get? You're going to get negative 0.062 to 0.162. Is it plausible there is no difference in the proportion between smokers and male and female? Well, remember what it means to be no difference. No difference indicates a zero value. The question is zero inside of this interval? And the answer is yes. So for the reason I just stated, yes, it is plausible that it works. A sample of 46 with a mean of 13.6 is used to construct a confidence interval level for mu. A bootstrap distribution is based on 1,000 samples and created. Where will the bootstrap distribution be centered? Remember, the bootstrap distribution is always centered where the mean value is located, 13.6. In a recent poll of 1,000 American adults, the number saying the exercise important part of daily life was 623. Answer the following questions. The original sample mean. The original sample mean is right here, 0.623, because remember, this is the original sample. The center of the bootstrap is approximately this 6.23 value right here. This number that it's showing right now is from a statistic that was given. The size of the bootstrap sample is, this one is 1,000 right here, 1,000. And lastly, the standard error. Okay, well, we need two standard errors. Notice we have a line here, as it looks like that's about 65. So if we started at 635, we've got about 0.15 for our standard error. 0.015, because remember, there are two standard errors here, and there are two standard errors here, and the split between there would be approximately 0.03 in change, and half of 0.03 is 0.015. The estimate for the 98% confidence interval is somewhere between. Okay, well, in the calculation for this, I have to look at this and say, okay, 98%. There are 1,000 dots. So since there are 1,000 dots on the piece of paper, I have to know there are 2% left over from 100%. And if I divide 2% by 2, I get 1%. 1% of 1,000 is going to cause me to cut in or count in 10 dots on each side. 1%. Just wrote that incorrectly. Give me 1 second. Oop, there we go. I can fix it still. 0, 1. There we go. There's 1% times 1,000, because there are 1,000 dots on the paper. So you take the number of dots times the percentage. That's going to equal approximately 10 dots. So from each corner, I'm going to count my way inward approximately 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. So I'm somewhere around right here for my first one. And I'm going to come in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to be right about here. Now I'm making a guess, if you will, and it's going to be a guess. So I'm going to go 0.588. I'm breaking up the number line there, and I'm going about to 0.659. Again, I'm using the percentage against the number of samples, and I'm using that to get the number of dots to move in from the outside. A biologist collects data on random samples of porcupine. She wants to estimate the correlation between the body mass of the porcupine in grams and the length of the porcupine in centimeters. Her sample consists of 20 porcupines. A bootstrap distribution for the correlation sample of body mass based on 1,000 samples is provided. The sample size is, she collected data from 20 porcupines, n equal 20. Would it be appropriate to use the bootstrap distribution to estimate the 95% CI for the correlation between body mass and length of the porcupines? And if I look at this picture, the answer is going to be no. Why is it going to be no? Look how heavily skewed the curve is. It is skew left. The data is not symmetrical. We would not use it for a distribution. In number 15, we have a couple of different questions being asked of us. Use the information in the table to construct a 95% CI for the difference in proportion of those who agree between males and females. So first of all, I have to look at the males who agree. So if I look at the males who agree, there are 372 out of 1,213 males who agree for a 0.307 percentage. When I look at the females who agree, that is 363 out of 1,412 for a 0.257 agreement. It's asking me, first of all, to take the proportion difference between males and females. So I'm taking 0.307. I'm subtracting 0.257. And that's going to give me a grand total of 0.05. Then I'm supposed to use the standard error. And remember, we use two standard errors in order to do a calculation. So I'm going to take 0.05. I'm going to add and subtract two standard errors of 0.05 for a grand total of, or a CI of, 0.014 to 0.086. We're going to run through these kind of quickly. To select a bootstrap sample, we sample with replacement from the original sample to get a new sample of different, I don't think so, size. False. A bootstrap statistic will always give the exact, I don't think so, answer. We can estimate the standard error by using the standard deviation of the bootstrap sample. Yep, that's why we do it. Constructing a 95% CI for a parameter based on sample statistics and the standard error from a bootstrap distribution can only be used when the bootstrap distribution is symmetrical and bell-shaped. Yep, because we just threw one away that was no good. As you increase sample size, the statistic calculated is the same estimate. No, remember, the more n values you have, the better the data. As you increase the sample size, the width of the confidence interval decreases. Absolutely, positively true. As the level of confidence increases, the width of the confidence calculated will increase. Well, yeah, because it goes out and so does it. So does both values. The interval estimate for mu minus mu2 using x1 minus x2 is 15 with a margin error of 2. Is from 11 to 19. Well, first of all, if you had this value, that is not a standard error. It says margin of error. You would not double that value. So you would not take 4 from the top and from the bottom. So the answer to this is false. Remember, you only double when there's a standard error, not a margin of error. The 95% CI for proportion of 0.74 to 0.87. The p-value of 0.95 is a plausible value. False, because 0.95 is outside of that CI. Remember, it's plausible if it's within the parameters of that range. Assuming the sampling distribution is symmetric and bell-shaped, if we have a p-hat value of 0.29 and the standard error is 0.4, then the 95% CI is from 21 to 37. That's a good distribution because remember, it's 0.29. We have a standard error, which is going to be plus or minus 2 times the standard error of 0.04, and you will get 21 to 0.37, and you will have a true problem. To create an 85% CI from a bootstrap distribution using percentiles, we should chop off 7.5% from each tail. True, because remember, 7.5 and 7.5 make 15%, and 15% and 85% make 100%. If our bootstrap distribution contains 1,000 bootstrap samples, to create a 90% CI from a bootstrap distribution using percentiles, we should chop 10 values off of each n. If we are creating something with percentiles, we do not chop off values, we chop off percentages. This is false. The parameter and the statistic we are usually interested in for a single categorical value would be p and p hat. Now, I've got a different piece of paper here that has a completely different question, but I'm going to look at what I have here. The parameter and the statistic we are usually interested for a single categorical variable is p and p hat, and we would have a true notation for something like that. I also have a question sitting in front of me, which is different, which says, an interval estimate is believed to contain the actual values of the parameter. That would be true. So if you have the version, we have several versions running around of the review, that version would be true for you. And true for you either way, pretty much. Ooh, that thing just went crazy, didn't it? Right there. N, an interval, yeah, I'm on N now. As you increase the bootstrap sample from 1,000 to 10,000, the width of the confidence calculated will increase. No, it will decrease. It's false. And the 95% confidence interval means that 95% of the intervals constructed will contain the population parameter. Absolutely, positively true. Moving on. Number 17. A random sample of n equal 1483 adults in the U.S. were asked whether they consider a car a necessity or a luxury, and we find that 95% CI for the proportion saying that it is necessary is from 0.83 to 0.89. Choose the correct interpretation within the context of the problem. Well, the correct interpretation of this would be we are 95% sure that the true proportion of all adults in the U.S. who think the car is a necessity is between 83% and 89%. Make sure you have all those things that I underlined. Number 18, suppose 95% CI if the mean score of a fitness exam goes from 63 to 73. Based on the original sample of 30, and the Bootstrap distribution contains 5,000 samples. For each, describe, indicate which of the CIs would be most likely results. Okay, so if we're using the data to find a 99% CI, so you have to do some calculating in order to get a 99 CI. Remember, you're going to take 1% is going to be left over, and 1% left over is going to be something which is smaller. So we went from a 95% CI having these numbers. These numbers are going to have to get left of this and right of this, meaning 73 has to get bigger and 67 has to get smaller. The only proper answer here is A. In letter B, if I go to a 90%, I'm dropping down, which means the CI is going to shrink. As the CI shrinks, the numbers have to come inward. So 67 has to get closer to 73, and 73 has to get closer to 67.5. Remember, the CI is shrinking slightly, whereas here, the CI was growing. In letter C, we're now increasing a sample size of 45. Remember what happens when you do 45? You are going to shrink that CI, or when you increase N. Letter D, we're using an original sample size of 16, so now we decrease the sample size from 16. We're going to blow up the number, and we're going to make it get larger, because remember, our data gets more loose when we decrease N. And the last one, using 10,000 Bootstrap samples from the distribution, which is the same that we used before. Nothing's going to change. It's going to stay the same, 67 to 73. Make sure that you are well aware of all of these calculations. On the key for this exam review, we have given you all of the typed out formulas when we did the actual statistical review answers. So make sure you take a look at those, even if I don't show those on the board. True and false. An event is a subset of a sample space. True. If A equals 0.7, then P not of A is 0.4. That would be true or false. It will be 1 minus 0.7. It would be 0.3. P, if A and B equals 0, the event A and B is disjointed. Absolutely, positively true. The experiment is drawing a red card from a standard deck. The number of possible outcomes in the sample space are 52. That is correct, because there are 52 different cards in a standard deck. The probability of event A is measured as the likelihood of event A. True. The probability of A if B equals the probability of B if A. Absolutely not. You see that one? You know that is not true. Two completely different formulas. We would never have two formulas if they were the same thing. Letter G, two events being disjointed and two events being independent are equivalent. Those are not the same thing. Otherwise, we'd use the same word. Event A and B are independent if two events have no effect on the occurrence of each other. Yes, that's the definition for being independent. And lastly, if A and B equals the probability A times the probability of B, then the events are independent. That is a true statement. That's how we actually check. Question number 20. For two events A and B, we have probabilities listed of 0.47, B is 0.33, and A and B are 0.2. Round your answer to 2 decimal places. If we are doing the finding probability of not A, so first of all, not A, we already know A to be 0.47. So it would be easiest if we were to calculate 1 minus the probability of A, which is 0.47, do the subtraction and get 0.53. In letter B, find not B. Well, we're going to do the same thing. We're going to take 1 minus 0.33. 1 minus 0.33 is equal to 0.67. And letter C, find the probability of A or B. Well, first of all, we need the calculation of A or B. So we go back to the formula sheet right here. And at the bottom, where the formula sheet is at, it's at the bottom of the page, A or B right here, we take the probability of A and the probability of B, and we subtract A and B. So if you look at what we have the probability of A, 0.47. I lost it for a minute. Plus the probability of B. The probability of B is 0.33. Subtract the probability of A and B, which is 0.2. 47, 50, 80 minus 2, 0.60 or 60%. Letter D, find A if B. Well, remember, A if B means the probability of A and B divided by the probability of just B. Well, probability of A and B is 0.2. Probability of just B is 0.33. And if you divide those two things, you get 0.61. B if A. Now you just simply have to turn around what you are dividing by. It will still be A and B in the numerator, but now in the denominator, it's the probability of A, which is 0.47. Division on that product will give us 0.43. Are the events A and B disjoint? The answer is no. Why is the answer no so quickly? Because A and B says that you have a probability of 20%. You can't be disjoint if you happen to have a value. From a table, give the following table, find the probabilities and round your answers to 2 decimal places. All the same exact things will happen, but now we have to do a little adding. For instance, for probability of A, I have to add 0.2 and 0.1 to get 0.3. To get the probability of not B. All right, well, not B, 0.1 and 0.3 make 0.4. Not B. Find the probability of A and B. Change my color. A and B happens only right here, 0.2. Find the probability of A or B. Okay, well, now I have to do a little bit more work here. So remember, I need the probability of A, 0.3. I need to add this probability of B. The probability of B is 0.6. And I have to take away the probability of A and B. 3, 9. 9 minus 0.2 is 0.7. Find the probability of A if B. Well, A if B, if I look at A given B, now a couple things can take place. First of all, I have to have A and B, and the probability of A and B is 0.2. Then I have to divide by the probability of B, and the probability of B was 0.6. 0.2 divided by 0.6 rounded is 0.33. If I turn that around, it's still 0.2 for the numerator, but now it's being divided by the probability of A. The probability of A was 0.3, and this is 0.67 actually, because it's 6666 or 0.67. Are A and B disjoint? And the answer to this is no. Again, how do I know there's a no? Because remember, there's an A and B and it equals 0.2. Are events A and B independent? Well, the first thing I do is I take the probability of A and I multiply it times the probability of B, and then I look to see if that equals the probability of A and B. That's how I always test. Okay, well, the probability of A is 0.3 times the probability of B. The probability of B is 0.6. And I look at the probability of A and B, and it's 0.2. When you multiply 0.3 times 0.6, you do not get 0.2, so therefore the answer is no. It would be, if they equaled the same number, then it would be yes. Find P married if less high school. Okay, so I want the probability that I am married given the fact that I have HS. Okay, so I have to go find those. So first of all, I have to go find in here married, right here, given high school. So I want the intersection of these two values right here. If I look at the intersection of those two values, I remember in my formula, I want the probability, first of all, of the and. The and is 70 out of 665 because it's out of all. For the denominator, I have to divide by the probability of HS, or high school. The probability of high school was 125 out of 665. 125 out of 665 for a grand total of 0.560. Chapter 4. A type 1 error occurs by not rejecting the null hypothesis when the null is actually true. A type 2 error is the not rejection of the null when it's actually false. The definition of a p-value is the probability when the null hypothesis is true, that's always important, of obtaining a sample as extreme or more extreme than the observed sample. Letter C. In the situation below for 26 and 27, describe what it means to make the errors of type 1 and type 2. So in the first one, making a type 1 error. Remember, if we go back to the type 1 error very quickly, and we look at that definition, the type 1 error is the rejecting the null when the hypothesis is true. So the only one here where that takes place is that we sue the company, so we effectively do something when they actually were not lying. The null was true. Nothing was happening, but we rejected that nothing was happening. In the second one, remember, we're going to act on something that we really shouldn't act upon. In this one, we're going to let the company off the hook when they actually are lying about something. It's a failure to reject, if you will. Number 28, if the significance level is 5%, which p-value provides more evidence against H of O? You always want the smallest value you can find. Always the smallest value. The hypothesis H sub O, p equals 0.8 versus H of A at p less than 0.8, so this is a left tail test. The outcome is based on n equal 10 observations, and we have a p-hat value of 0.7. And the randomization statistic to be calculated is p-hat. The p-value for the test was found to be 0.322. If the test was performed correctly, where should the randomization distribution be centered? Well, the randomization is always centered at the null hypothesis. There's a lot of reading for something so simple. In number 30, an article published in the Canadian Journal of Zoology presents the method for estimating the percentage of body fat in North American porcupines. The method was illustrated in the sample of N25 porcupines. Based on the sample, a 95% confidence interval level of body fat is 17.4 to 25.8. Which of the following null hypotheses should be rejected based on this confidence interval level? So look at the range of 17.4 to 25.8. Which value is outside of that? Letter B, and because letter B is outside of that confidence interval level, we should reject it. Number 31, the following distribution is given for mu of S equal mu of, I think, L. And H of A is not equal, so we have a two-tail. Find the p-value. Okay, well, notice that this is a p-value. But at the same time, because it's two-tailed, this is a p-value. So it's 2 times the p-value of 0.31. Our p-value is 0.062. That happens, we always double when we run a two-sided p-value test. Number 32, a statistic test is conducted to see if there's evidence that the proportion of U.S. adults who own tablet computers is greater. I'm going to circle that, greater. And it's greater than a mu value of 0.5. Or not a mu, excuse me, a p-value of 0.5. Which one of these provides the most significant evidence? Well, the one that's going to give us the greatest, the highest number over 0.5. Because remember, what we're trying to find is we're trying to find things that are this way, very far away. Well, that's going to be the one with the highest count, and the highest count is going to provide the highest proportion, and we are going to get sample B. If we were on a left tail test, we would look for the smallest value. A statistical test uses data from a sample to assess a claim about a population. True. The larger the p-value, the greater the evidence. That's false. It's the smaller p-value. A p-value should be between 0 and 1 inclusively. So in other words, it should be somewhere from 0 to 1. That is true on a p-value. It is false on an r-value. For a significance level of alpha 0.05, the decision for a p-value of 0.004 is to reject h of o. That would be true. It's smaller. You reject on a smaller value. Do not reject h of o is the same as accepting h of o. We never accept h of o. False. Statistical significance is not the same as practical significance. Again, two different words, two different meanings. Replication of a study with similar conclusions gains credibility. Absolutely. That was in the lecture slides. The center of the randomization distribution is centered around the sampling statistic. Not true. It's around the null hypothesis. It's the bootstrap that is centered around the sample statistic. If a 95% CI misses the parameter h of o, then a two-tailed test should reject h of o at an alpha level of 5%. Absolutely, positively true. The larger sample size makes it easier to get significant levels. Absolutely true. And the confidence intervals for estimating the value of a parameter, while the hypothesis test tests whether the data provides evidence. Very good words there. Evidence for h of o, and confidence interval is just looking for estimations. Number 34, indicate the analysis involves a statistical test. Letter A, a polling of 800 people in a large community to determine if there's evidence, I see the word evidence right there, for a claim of a mobile home is greater than something, and the answer is yes. Letter B, utilizing a census. Remember, a census includes everybody. You just ask them all. There's no statistical test to perform here. All you're doing is collecting data. Use the following to answer questions 35 through 38. The evidence against the null in favor of the 20 is very strong. Go find the smallest number you can find. Letter B. The result is significant at 5%, but not at 1. That means it is smaller than 0.05, but it is not as small as 0.01. That is letter D. There is no evidence supporting the alternative hypothesis. Well, if we look at that, that's letter C, because it's 0.6. That thing is so big that we wouldn't even think about getting rid of it. And the last one, the evidence against the null is significance, but only at a 10% level. This one here is just barely below 10%, so it makes 10%, but it doesn't make 5, and it certainly doesn't make 1. Identify the following hypothesis as valid or invalid. The first hypothesis, first of all, not valid. No. Why not? Because it uses statistic data instead of mu data. It would have to have p-value is equal. Letter B, the hypothesis is mu does not equal. It never starts with does not equal. The hypothesis h sub o is 2.5 and h sub a is greater. We'll take that one. The hypothesis h of o, p equal 30. Can't have it. Why not? Because a proportion can't be bigger than 1. The hypothesis, the mu is 2.5 and the h of a is greater than 2.5. So I'm looking at this one and I'm looking for something. So I got a mu value of 2.5 versus an h sub a where the mu is greater than 2.5. I want to say I've stumped myself for a second because I'm thinking about the next one, the P1 minus the P2. But remember that when we start a mu value for the hypotheses, the H sub O is 2.5. And my speaker is going crazy right now. Give me 1 second. And the secondary mu value, H sub L, is greater on a 2.5 level. So the hypotheses would be valid. The P1 minus the P2 equals 0, and the P1 minus the P2 does not equal 0. So in this, we have a yes value. Yes value. And the last, not the last one, the hypothesis of P, or rho, 1.05, that one's no good because rho can never go above 1. Remember, this is a correlation, and correlations always have to be smaller. And the last one, H sub O, where P1 equal P2 and P2 minus P1 is less than. This one is no good because we changed the order of what was going on in the values, and we can't take and change the order of what's going on in the values. Moving on, I'm going to stall for 1 second because I have to start this video and it's getting a little long, so give me 1 moment, please. Okay, I'm back. I got the video going, and I don't think I finished answering letter E right there. Go finish that one. And I did put a line in that. I kind of stumbled around on that one, and I didn't identify it for you correctly. Now, remember, you're allowed to have an equal, but remember, you're not allowed to have an equal in this one. Okay, so that would be a not valid. Now, if that were just a greater than, and I think that's what I was indicating, is that if it was greater than, then we would have a good number right there. Number 40. Let's keep going. So indicate whether whether it is best assessed by using a confidence interval or a hypothesis test. A proportion of people using public restrooms wash their hands after going to a bathroom. You are not testing anything. You're looking for an average CI. The proportion in 2010, what percent of U.S. Senate voted to confirm Elaine Kagan? Well, this is just a measurement. There's no statistical test here. We're just counting heads. Do a majority of adult riding a bicycle wear a helmet? This is a hypothesis test. We have a thought in mind, and we're going to conduct a test to see what happens. On average, how many more do adults who play sports in high school exercise than adults who did not play sports? Again, this is a range. This is a CI, just how many more. And what's the average daily calorie intake of a 20-year-old? And again, a CI. Unless you're seeking evidence, you're not doing a hypothesis test. Number 41. Let mu be the average amount of sleep a student gets per night. Data was collected on a sample of students for X bar equals 6.7. A Bootstrap distribution provides a confidence interval level for mu and a randomized distribution to see if the data provide an evidence that mu is greater than 7. Which one of these is the Bootstrap distribution? Well, remember, the sample is at 6.7, and the Bootstrap is always on 6.7, so your winner is the one that's centered at 6.7-ish. If I go down to the next one, it's the same exact question, but it wants to know about the random distribution. The random distribution will center itself at the mu value. Remember that the mu value for this one, it was testing the alternative greater than half, which means that H sub O would have been P equal to 1/2, and this one is centered up at 1/2. Number 43. A random sample, a random sample. I'm reading the wrong one. Given H of O, P equals 0.4 versus H of A, P is greater than 0.4. 4 possible statistics along with 4 possible p-values given. Match the statistic to their p-value. Okay, well, a little bit of drawing time here would definitely help us. For instance, the center is approximately here, 0.4. And it looks like that I gain about 0.1 on each standard error. So what I'm producing, and I'm going to shade underneath, is the approximation for the 95% of the data that's being held under the curve. It's very likely that things happen when they're underneath of there. So for my first statistic, 0.3. Oops, undo. Go back to the pencil. Let's do an undo. Let's get a pencil. There we go. 0.3. So I go find 0.3, and 0.3 is dead on right here. Okay, so that means that I'm looking, first of all, on a p-tail test, which is going to be less than some number. So I'm going to have a very small percentage of values. When you're looking at a p-value, you're looking to see how much of that area is greater than to the right side tail, because remember, this is a right tail test. Right tail test. So we're looking to see how much area would I have associated with that. Okay, so I'm going to shade from 0.3 all the way up to the right. Well, that's a lot of area, right? Matter of fact, it's 50% and more, because remember, the middle contains 50% going to the right. So I have to have a number greater than 50%. This is the only number greater than 50%. Letter A has to go with that one. I'm going to now go back and get rid of some of that shading so that I can hopefully do this all over again. So I'm going to redraw again one more time and pretend all the same stuff is up there. So now I'm going to the next one, a 0.42. Okay, well, I'll go find a 0.42, and it's just a little bit to the right-hand side of the center. Okay, so it's a little bit less than 50%. Now I got to find a number a little less than 50%, and there's my number that's a little less than 50%. I'm going to go find myself another number, 50%, dead on, or excuse me, p-value 0.5. 0.5 is right here. Now remember, I'm moving further away from the 50%, so the percentile is coming down. It's not real small yet, but if I'm not quite sure, let's go grab the other number. Let's go grab the 0.65. 0.65 is further out. It's out here somewhere. It's going to contain a much smaller p-value. So right now, if I compare the difference between these two things, the smaller p-value is clearly 0.062. So I would put the d value here, and then that would leave me with the only statistic left, which is the c value for this one. Remember, the further you move away from the center, the lesser the p-value. The closer you are to the center, the more p-value. In a hypothesis test for mu equal 12 and mu less than 12 for h sub a, we have a sample of 45 with an x-bar of 10.5. What do we require about the method to produce the randomization? Remember, the randomization center happens to work at the mu value. So we need to know that mu is 12. Where will the randomization be distributed? Or where will it be centered? At that same location, 12. What will we look for on the randomization distribution? Well, we're going to look to see how extreme the produced value of 10.2 is going to be. We're going to look for the p-value that associates itself with 10.2. Number 45 in a same kind of hypothesis test. Now we have mu1 equal mu2, and we have h sub a greater than mu1 compared to mu2. So we are centered up at the difference between mu1 and mu2. The first thing we would talk about is, what do we require? We need to know what is the difference between mu1 and mu2. And we know that if we subtract these two things, we're going to get a 0. Where will the distribution be centered? It will be centered at that position of 0. What do we look for in the randomized distribution? Well, remember, 26 was your first value and 21 was your second value. Since we're testing in an environment that says mu1 equals mu2, that means mu1 minus mu2 equals 0. We have to take 26 minus 21, and we are testing when 5 is more prevalent. Letter E. Without finding a p-value on stat key, which sample provides the strongest evidence? Well, oops, sorry, I missed one. C. I missed one. What do we look for on the randomized distribution? Oh, no, I got that. I put the 5 around the wrong one. How extreme is 5? I wanted from right there. Thought I missed a question. Without finding a p-value, which sample provides the greatest, strongest evidence for a right side tail test? Well, right side tail means I want the biggest number to be possible. They're all the same, but one of them has a much larger n value than the others. This one has an n value which is 100 times that of the smaller ones. Large n value rules. Number 47, it is believed that sunlight offers some protection against multiple sclerosis. All mice were injected with proteins known to induce a mouse form of MS. Researchers randomly assigned mice to either one group, a control group of UV light. The scientists found the mice exposed to UV light were significantly less. That means small p-value. But the vitamin D did not reduce the likelihood of getting MS compared to the control group. Okay. One p-value is 0.47, the other is 0.002. Which p-value goes with which test? Well, the UV was significant. So the significant one is 0.002. Remember, small is significant. Therefore, the vitamin D value is the non-significant, which is 0.472. The provided figure has a randomized distribution for mu of 100. We can see the middle. The p-value for the sample at x equal 118. So we go find 118, which is way out here. And we were testing to see for a right side tail test greater than right there, we're going to have an incredibly small p-value because I don't even see any data out there. Question number 49, I believe. This is the cat one. I think we go over this one in class, actually, and it talks about the percentile of calculations happening. So it said, could owning a cat as a child relate mental illness? So we did this actually in class. So there are two things going on here. First thing going on is that, and as you take the time to read through the question and come back to it, randomly selected 262 people right here, registered with the Alliance for Mentally Ill. 136 of those 282 had a mental illness. 220, change my color, of the 522 did not have one. So the question comes down to, what's P1 minus P2? Well, that means 136 out of 262, that's my first statistic, minus 220 out of 522. Now, I highly recommend that you stop, take a minute, and read that question thoroughly. But we also covered that one in class. 0.098. For testing the H sub O and the H sub A. Okay, so H sub O, nothing going on, would indicate to us that the proportion of the first is equal to the proportion of the second. The H sub A would say that we are looking to see if P sub 1 is greater than P sub 2, or the proportion. Find the p-value rounded to 4 decimal places. Okay, well, look at the graph that's given to us, and we can see right here that we have a 0.098 value. That's the p-value of things which are greater than. Take that value take that proportional value and test it against our value. So what we're going to do is we're going to look at the sample size of 600 people. In 600 people, we're going to multiply those numbers together of that proportional difference of 0.098 and those 600, and we're going to get approximately 0.0033. That's going to be our approximate p-value, and we do not double that p-value because why? Because it's a right-hand side tail test only. You can also confirm this inside of StatKey if you want to go in there and mess around with it and see what that is. The hypothesis for statistical tests are given. So first of all, H sub O is that P equals 0.8 and P does not equal 0.8. First of all, if we had a 95% confidence interval level and it went from 0.63 to 0.84, what would we do? Well, remember, we have a 0.80, right? And 0.80 is inside. We do not reject. What's the significance level? 5%, because 95 subtracted from 100. The next significance level is also 5%. We look at the data, and the data is from 0.98 to 104. This time we reject because the value is outside of the CI. The last one is a 1% significance level. And in this one, again, 0.76 to 0.94, it is in there. We do not reject H sub O. Number 51, a certain species of trees has an average lifespan of 130. A researcher has noticed a large number of trees of this species washing up along the beach. She takes a core sample of 27. There's the sample. Of those trees, counts the number of rings to measure the rings. Counting the rings also allows the researcher to determine the age of the tree. The average age of the tree samples from about 120 years. Okay, well, that's important right there. About. There's my average. One of her interests is determining if the sample provides evidence, so it's a statistical test, on the average age of the driftwood, which is less, left side tail test, of 130 years. So the one she has is 120, and she's testing this. If the average age of the tree is 130, might suggest the trees have died. First of all, state the sample size. Well, the sample size is 27. What's the statistic? An average of 120 years. What was the null and the alternative? Well, the null is that H sub O says that the average value is 130. And the H sub A says that the mu value was less than 130. What is the direction of the tail? It's left because it's a less than. State the center. The center is the mu value at 130. If we have a p-value of 0.08, what is the conclusion for a 10% test? 0.08 is smaller than 10%, because 10% is 0.1, so therefore we would reject at that significance level. 52, the owner of a small pet shop wants to second store in another city, but only wants to do so if it is more than 30% of the city's household pets. Otherwise, there won't be enough business. He samples 200, and he finds 70 have pets. State the null and the alternative. Well, the null is that the p-value, or the proportion, is 0.3, the H sub O. The H sub A is that the p-value is greater than 30. That's what he's testing for. What is the sample statistic? Well, it was, I have to find it, and he finds that 70 of them actually have pets. So the 70 is going to get divided by the 200. So the sample statistic is p-value hat is going to come from 70 divided by, 200. So we have a 70 divided by 200 value. Normally you want to compare that into a decimal at the same time. I'm grabbing my calculator right now. And I'm getting 0.35 for number, what number are we on right now? Number 52. So 0.35. 0.35. So my p hat value equals 0.35. Got it. I keep going on number 52. And the question says, what does the question say? Letter D. Write the conclusion in the context of a 5% value. Okay, so again, we wrote these down for you, and you can read them directly, but we do not reject the null. There is no evidence that the proportion of pet owners in the city is more than 30%. More than 30%. Also, it wants to know, I think I skipped over the p-value. Okay, well, remember that the p-value, first of all, we're going to look for the number of dots from the sample. Our sample was 0.35, so we're going to count these dots over here. How many dots do we see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 dots. 15 dots divided by 200 dots. 15 dots divided by 200 dots is approximately 0.075. That's a very valid way of doing a p-value when you have dots. That was what I would say is a great speed review, people. Please take the time to look at all the things we've done. This should prepare you very well. You won't see nearly as many questions on your exam. However, at the same time, though, you will see these styles of questions. Hope this has been helpful to you, and I'll see you soon.